Okay, good morning, everyone. Thanks for coming. And let's start. So today we're going to talk about the detailed implementation for the training algorithm of support vector machines, right? So we mainly call this the primal training because right now we're still viewing support vector machine as a linear classifiers. Right? So what we have discussed so far, we'll talk about the principle about support vector machines, right? So we started with the generalization error bound derived based on VC dimension and agnostic learning setting. And then we can show that if we can smartly select the subset of linear classifiers, know that this subset linear classifier is not entire family of linear classifiers. And if you can still get a good training error, the benefit is that, okay, because you're reducing the family of linear classifiers, you can still reduce the VC dimension. And as a consequence, you can tighten the generalization error bound. So that's the key idea. And there is some like a connection between the margin and the VC dimension. It is called data dependent VC dimension. Basically, if you want to identify a set of linear classifiers whose margin is at least gamma, there are some theorem showing that this VC dimension for this set of linear classifiers is inversely proportional to the margin. So that means the larger the margin used to select this set of linear classifiers, the smaller the VC dimension. That's why we directly derive this learning principle. That is, we want to maximize margin, right? And from that, we kind of formulate the SVM objective, right? So the naive objective function is just to calculate the margin of the current linear classifiers in the inner loop, and then in the outer loop, you will maximize the margin. But there's some problem with this because this is maximum optimization, right? We can refresh our mind, right? So then we kind of leverage the properties of linear classifiers. That is, you can arbitrarily skew the model parameters of linear classifiers, say by 1, 10, 11, or 1000, 0.001. They won't change the linear classifiers. So to avoid explicitly computing the margin, we'll kind of like consider, okay, we're focusing a set of model parameters such that its function margin is 1, right? So by putting these constraints, you're looking into a subset of model parameters, but these subset model parameters are expressive enough to cover all kinds of linear classifiers. We really do not need to search over the entire parameter space to identify the optimal linear classifiers. You only need to you only need to focus on a subset of linear classifiers, because all the other model parameters they can be by multiplying some scalar, right? You can find out a set of parameters in this subset which is equivalent. So that's the key idea. I'm not gonna like go through all the slides we have previously discussed. I want to use this quick description to refresh our mind and to push our on the right track. So here, I mean, after this kind of formulation and simplification, and also we can remove the additional slack variables we introduced, we come to our SVM objective function. So here we can see the objective function consists of two components. So the first component is this half W transpose W, right? In the SVM context, it means we want to maximize margin, because the margin is actually, if we could remember, okay, it is 1 over the norm of W, right? Hey, remember, in our SVM formulation, we require that the functional margin, namely the numerator of the distance of all the data points to the hyperplane, its minimum is 1, right? So then that means the margin becomes 1 over W norm, right? So you want to maximize the margin, you are essentially minimizing the square norm of W, right? So the second term which is derived from the constraint, right? The introduction of slack variables, if we could recall, right? So we introduce slack variables to allow some data points to break into the margin. Some data points are excluded from the margin, right? So if you kind of simplify this term and get rid of those slack variables, we have this term, right? So this, as we discussed in the last lecture, is called a hinge loss. It actually describes how well your current model fits every training example, right? We'll talk about this interesting loss function. You see that when you make a correct prediction, we'll make wrong prediction, obviously, this hinge loss will be non-zero, right? It's bigger than zero, meaning that, okay, you're gonna bear with some like penalty, right? But if you make a correct prediction, however, if your data point is not far away, in other words, like if your hyperplane is too close to the data point, you can still get some penalty, right? Because this is hinge loss. This property of hinge loss requires that you're not only correctly predict the example, but also you want to adjust the hyperplane to be far away from every data point, right? That kind of push your adjustment of hyperplane to have as much larger as possible, as large margin as possible, right? That's the idea. Right? Okay, so basically, this structure, the structure of this loss function reflects some kind of new learning principle, which we call structure risk. Sorry, it's a regularized structure risk minimization principle, right? So we have some regularization term to penalize overcomplicated hypothesis space, and we have some loss term which look at how well you can fit the training data, right? We want to find the best trade-off between the two so that we can have the minimum generalization error, right? So that's the key idea. Okay, the goal of today's discussion is to talk about how do we efficiently minimize this objective function to find out our model parameters W and B, right? Remember, W is the weight vector for all the features, and B is the bias parameter. Okay, so any questions so far? Hope everyone is on the same page. So now we're going to talk about things about today's class, right? So so here is the outline about how to train SVM by optimization. We're gonna first review the concept about convex function and gradient descent. Actually, it's fairly easy to show the SVM's objective function is a convex function. That's why we would like to review the basic definition of convex function and properties and how do we optimize this function, right? And we'll introduce the we'll review the gradient descent framework we discussed before. Remember when we talk about least mean square regression, we use gradient descent framework, right? So we can leverage gradient descent framework again. However, our focus will be a stochastic version of gradient descent, which is called stochastic gradient descent. We'll explain why it is preferred in nowadays machine learning, especially in a scenario of big data. Right. And then we'll talk about we'll compare gradient descent and stochastic gradient descent, right? The pros and cons and contrast their behaviors. And then we'll apply the stochastic gradient descent framework to optimize the SVM objective function. But later we'll see that the hinge loss itself is not differentiable. Okay. It's actually a piecewise function, right? It's not differentiable. And in that case, like regularly speaking, you cannot calculate the gradient. Right? Then how can we address that problem? We're gonna introduce this concept called sub-gradient or sub-derivatives. And we're going to use sub-derivatives as a substitute for derivatives to conduct the stochastic descent, gradient descent. And finally, we're going to compare our learning algorithm with the perceptron algorithm we discussed previously. So if we could connect back to the perception discussion, we know that perception is kind of like a lazy learning, right? Every time I look at the current example, I try to use my model to make a prediction. If my prediction is correct, I don't do anything. I do nothing. And if my prediction is wrong, I apply some kind of heuristics to update the model, right? So we'll see that this whole procedure, including no updates and those heuristic updates, can be viewed as a particular type of subgradient for some loss function. So in other words, perception can be justified by some stochastic subgradient descent framework. So now we can connect SVM and perception, right? They're both for linear classifiers. Right? The only difference is the objective function formulation. And but they both can be viewed as applying the stochastic subgradient descent for the optimization and the learning. Okay, we'll get to that point later. Okay, so first review of convex function gradient descent, right? So if you look at the SVM objective function, it's pretty easy to show this is the convex. Why? You can see that there are two terms here, right? So the first term is a quadratic function. So quadratic function is a typical convex function. Why? Can anyone come out a one sentence proof to show this? Why this quadratic function is convex? Right, right. So if we consider general a function f of x, right? If it is twice differentiable, remember there is a very important property, right? If f of x is twice differentiable, then if we can show that the Hessian of Hessian basically just means the second order derivative of f of x. If it is positive semi-definite, then this function is guaranteed to be convex. Right? That is one important property when we introduce the convex functions, right? So now if we look at this guy, so I want to ask what is Hessian? What is Hessian matrix for this quadratic function? Any thought? Any guess? It is just half of the identity, right? So if you take I'll leave it as an exercise for you guys, right? But basically, if you take a look at some quadratic function in this form, like x transpose ax, if you take the gradient, it will be 2ax, right? If you take the gradient again, it will be 2a, right? Right. So here it just means like a is identity, right? For the quadratic function. So the Hessian is just the identity, right? Of course, identity matrix is positive, definitely. So this guy is must be a convex function, right? Well, if you don't feel like comfortable about this, just look back at the definition of convex functions, their properties, and verify by yourself. We just want to emphasize. We just want to emphasize why this is a convex function, right? And for the second term, so you see that this is a linear function, right? Or Eiffen function. Eiffen function is always convex function. You do a max of 0, which is constant function. Eiffen function is this composition guaranteed to be a convex function. So add two convex functions together, it will end up with a convex function. So it's basically straightforward to show that this combination of several convex functions will end up with a convex function in the end. Any questions so far? Okay, so now for convenience, let us try to fold the bias parameter B into W. Right? So this is our notation sugar we introduced before, right? So we can introduce a new weight vector, which includes both the feature weights, which we denote by W0 and bias parameter. And then we augment each feature vector xi with 1, right? To account for the to accommodate this bias parameter. And then our SVM objective function can be rewritten in this form, right? So remember in the hinge loss, because we have this augmented data xi and augmented weight vector w. So now this function margin becomes yi w transpose xi directly. Right? And here to just emphasize that this w, right, actually corresponds to the original feature vector. So we use w0 transpose w plus this guy. Right? So then we now maximize the whole objective function with respect to w. Remember, w here includes both w0 and b. Any question? Right, then, yeah, let me emphasize again, right? So I just re-denote w. Remember, in the original formulation, w indicates the feature vector only, right? So now I'm using w0 to represent the weight vector for the features. And then I concatenate w0 with bias parameter b to form a new weight vector. So now this new weight vector w includes all the parameters. And then we can see that here w transpose xib now becomes w transpose xi, right? Because this new w includes both the bias parameter and the feature weight vector, right? And in the first term, because remember, this is just related to feature weight vectors. That's why we use w0 transpose w0, right? Okay. Yeah, well, that's good. Okay. So this just a definition of convex functions, right? I believe everyone's familiar with that. I just read through it. So a function f is convex if for every 2 data points in the domain and for every lambda between 0 and 1, then we have this convex inequality pose, right? So the basic says if you do convex combination of u and v in terms of lambda, and then evaluate at their combination, it will be less than or equal to you first evaluate f at u and v, and then do a combination of the function values. So that is called a convex inequality. So there are a lot of like associated properties of convex function. So one of the very important property of convex function is that if your convex function f is differentiable, then at any place, right? So at any place, say u here, right? And if you draw a tangent line at that place, the whole tangent line will stay below the function body. Right? So basically, like at this place, you draw a tangent line, you see that the entire body of f, this blue curve, stays above the tangent line. Okay? That's a very nice property of the convex function, and also forms the basis for our definition of subgradient later. So several commonly used types of convex functions. First, all the linear functions are convex functions. I mean, you can show this by yourself, right, to deepen your understanding of concept of convex function. Quadratic functions are convex, right? It's typical like this one, right? And also max between 0 and a linear function is convex. And also this guy, you can see this is like a 2-dimensional function, right? You got 2 variables, f is equals to x1 squared over a squared, x2 squared over b squared. This is a cone, right? This is a cone. This is also a convex function. So here an arbitrary function, right? How do we test whether this function is convex or not. So several common use ways. First, you can just use the definition of convex. Right? You need to show that for arbitrary two locations in the domain, this convex inequality holds, right? So this is the most general way of showing convexity, but it's in many cases a little bit non-trivial. Right? It's not very easy to show that. And the more commonly used ways methods are look at their gradient and also the Hessian. So if your function is twice differentiable, and if it's just one-dimensional function, meaning that your input is just the number, right, just a scalar, then you can calculate the second derivative. If the second derivative of the function is always non-negative, then the function is convex. If your function is multidimensional, meaning that it's a vector function, right, then the second derivative becomes Hessian. Then you need to show that your Hessian matrix is always positive semi-definite. If this positive semi-definite, then the function is guaranteed to be convex. Yeah, I want to emphasize that convex functions are just a very, very tiny portion of the entire family of Bally functions. Right? So many functions are convex. For example, if in the definition of convexity, if you just revert the inequality, those types of functions are called concave functions. So basically, you can turn all the convex functions upside and down, right? So it becomes a concave function, right? But there are many functions which are neither convex nor concave, like something like this, right? So basically, sine functions won't be concave or convex, right? Or this guy. It's not convex, it's not concave. In general, if your function is differentiable, and if we want to find out if we can claim that x is the minimum of function, so this minimum does not necessarily to be a global minimum. For arbitrary minimum of that function, then we can conclude that the gradient of the function at this position must be 0. But this is just a necessary condition. It means that if you find some arbitrary place, right, arbitrary input x, such that your gradient of the function at x is 0, it doesn't mean x will be a minimum of the function. So you see the difference, right? So if x is the minimum, then the gradient at x must be 0. But if the gradient at x is 0, it doesn't mean x must be minimum. That's why it's only called a necessary condition. It's not sufficient condition. So one example here. So if you take the gradient at this place, right? The gradient is 0. Unfortunately, this is not minimum. It's actually neither minimum nor maximum. So see that actually gradient being 0 is just the sufficient, just the necessary condition for you to find the minimum, but it's not sufficient condition. You can't conclude that, okay, when you have a 0 gradient, then you find the minimum. That's not correct. Okay, any questions so far? Everyone comfortable? Okay, so however, if we focus on convex function, things got changed. Things becomes a lot easier. So in convex function, you have zero gradient is equivalent to you have reached the minimum of the function, and equivalent to you have reached the global minimum function. So that's the nice property of a convex function. So basically, if you have a convex function, then the gradient being zero is both necessary and sufficient for you to find out the minimum. Any question? So we're going to leverage these properties to help us in the SVM training procedure. And this property relies on the fact that your objective function is a convex function. But if it's for a general function like a neural network or whatever other convex complex loss function, which is neither concave or convex and it's highly nonlinear, have many local minimums, all those properties won't hold. Okay, so now let's look back at the SVM objective, right? Remember here we use the notation simplification form, right? We fold the bias parameter and the feature width vector into W, and W0 represents the feature width vector only, right? So this is a convex function, and this is a particular type of convex function which is called quadratic function, right? That means like you can use some kind of mature algorithm to solve this type of convex function, which is called quadratic optimization. However, using quadratic programming to solve this convex optimization appears to be very slow. Especially you have a large number of features, right? You have high dimensional feature vectors, which make your training very slow. So we want to seek for another strategy, a very simpler to implement, but sufficiently efficient strategy. We can first consider gradient descent. Right? So we have leveraged gradient descent before in training the least mean square regression models. So let's review the gradient descent framework, right? So here's a general strategy. Suppose this is my objective function. Of course, in the SVM context, my objective function becomes this form, right? And then we're going to start with some initial guess for W, which we denote by W0. Then we do iterations. So we'll compute the gradient of the objective function at the current model parameter vector, WT. Then we'll update WT to get WT plus 1 by taking a step in the opposite direction of the gradient. That is why it is called gradient descent, right? Because the gradient descent indicates the decreasing direction of the function. This is we have used this figure to show why this is true, right? So suppose this is our G of W, and this is our objective function, right? And you start from W0. If you compute the gradient, that basically means that you're computing the slope of the tangent line at this position, right? So you can see that this slope is positive. And if you want to decrease the function, you want to minimize the function, right? You're going to go along the opposite direction of the gradient. That means because the gradient is positive, right? And that means you're going to move your W toward the left. Then you move it, you find that you indeed decrease the function, right? Then you calculate the gradient at the current position. You got a positive slope, meaning that you got a positive gradient. Now you update the model, parameters toward the opposite direction of the gradient, which is still on the left. You just keep doing this, you see that eventually you're gonna get closer and closer to the function minimum. Right? Any questions so far? G of W is just the objective function. Right? You want to minimize this objective function with respect to W. Does it make sense? What? Yeah, examples here. Right? This is a quadratic function, right? So here is our goal, right? We want to minimize this SVM objective function, right? But I want to illustrate that why should we use gradient descent, and why gradient descent can guarantee you to find out the function minimum. Right? So we use this like quadratic function. Well, it's regularly speaking, it's not necessarily quadratic, but it's kind of have like quadratic function shape, right? So you see that you start from here, the gradient is positive, right? Why is the gradient positive? Because the gradient is actually the slope of the tangent line here at this position, right? And your gradient is positive. Now we want to update the model parameters along with the negative or opposite direction of the gradient, right? So that means like, okay, you're gonna update your W toward the left, right? Because you're gonna decrease it. You're gonna decrease in W, 0. Right? Because your gradient is positive, right? You want to add your model, you add model parameters to like negative gradient multiplying some like step size, right? The negative means that, okay, you're going to subtract by some positive number. That's why your new W will be to the left of the W0, right? Yeah, then you see that, okay, we move to W1, you're actually decreasing the function value. Right? You see that here, right? W0 is here, and W1, the function value is here. You're kind of decreasing the function. Right? Yeah, if you just calculate the gradient again, you find that the gradient is positive, right? Remember, we're doing gradient descent. That means we're going to subtract the gradient by some factor, right? Multiplying with some factor. So meaning that, okay, you're going to continue move toward the left side, right? Going to continue decreasing the value of W1, get W2, keep decreasing the function, and doing this until you reach the minimum of the function. Does it make sense? Any question regarding this? What? Minimum? Yeah, that's a very good question. So basically, it's very hard to make sure of this. So in practice, what people doing is that, okay, I'm gonna just look at the norm of the gradient vector. If the norm of the gradient value is very close to 0, but it's very hard to conclude that it will be 0 because there are always some numerical errors, right? We're dealing with everything in a floating system, in a digital floating system, right? It won't give you exact 0. So what you need to do is that, for example, if you calculate the gradient, right, and you just look at the normal gradient, say less than 10 to minus 6, right? You will like, okay, I'm approximately being 0, right? So I stop here. But there must be some like a tiny difference between your current position and the real minimum. Another question? Okay, great. So now let us just apply the gradient descent framework for our SVM training. Right? So remember, this is our objective function, right? The quadratic term, which helps us to find a maximum margin, right? And the hinge laws help us to better fit the data. Right? So we initialize a model parameter, initialize our model parameters, and then we go through many iterations. In each iteration, we compute the gradient of our objective function at the current model parameters, WT. And then we just update our model parameters using the gradient descent. We subtract the current model parameters, WT, by the gradient, multiplying with some positive learning rate. Right? And that's it. And here R needs to be properly chosen, right? It cannot be too big. But if it's too small, you will see the learning progress is so slow, right? but it cannot be too big. If it's too big, it's perturbating too much. Okay, so now we have reviewed the basic concept of convex functions and the gradient descent framework. We know that our SVM objective function is convex, and we can literally apply the gradient descent to the training of our SVM model, right? And then let's proceed to the stochastic gradient descent framework, right? So why do we switch to stochastic gradient descent? If you look at the gradient calculation for the SVM objective, right, you see that in our SVM objective, the loss sums over all the training instances, right? This summation over I, meaning that we're gonna sum over every training instance. That means, like, if you want to calculate the full gradient, we want to go through the entire data set, right? We're gonna accumulate the gradient of the loss for every training example and add them together, right? So that will be very, very expensive when your data set is large. Like you have 1 billion training examples, which are not uncommon in today's scenarios, right? And in that case, like, you have to calculate the gradient for 1 billion times until you generate a final gradient, just a single full gradient. Use that full gradient to update your model for once. That's really slow. That's why in practice, people don't like it. We want to find out a more efficient way or cheaper way to update the model more frequently, right? Than just do gradient descent, because gradient descent, you have to pass through the whole data set once to get one gradient, right? So can we do this many, many times after we pass the data set for once? So this comes to the stochastic gradient descent. So how do we conduct stochastic gradient descent? Right? We're gonna first explain how to do that, and then justify why doing this is correct. Okay, so the basic framework is kind of similar. We're gonna initialize our model parameters as 0, and we go through big T epochs. And one epoch just means, like, you're gonna go through the whole data set for once, right? And inside each epoch, right, every time we're gonna pick up a random example, X, I, Y, from the training set S. Remember, S might consist of 1 billion examples, right? I just random pick up one. Right? Then I repeat this single example, X, I, Y, I, many, many times to fake a data set. This data set needs to have the same size as the original data set. Like, for example, the original data set S, it might have like 1 billion training examples. And then here we random pick up one example, right? I just duplicate examples for 1 billion times. So I fake a data set, which of the same size as original data set. Then we take the derivative of the SVM objective at current weight vector on this fixed data set, right? Because the whole data set only contains one unique example, right? You actually do not need to really duplicate those examples, right? You just need to calculate the loss function for this particular example and multiply for big N times, right? Big N here means the size of the original training set. And then plus the regularization term. Right? So here I will emphasize N here represents the number of training examples in the original data set. And then you just calculate the gradient of the total loss on the fixed data set and use that gradient to update the model. So this procedure is called a stochastic gradient descent. Any question regarding this procedure? I feel it's pretty straightforward. It's basically like, okay, every time I just random pick up one example, I just duplicate it for many, many times to fake a data set of the same size as the original data set. And then I calculate total loss on that fake data set, which essentially is just the normal regularization terms plus this number of training examples multiplying with the loss, right? Loss on this randomly selected example. And that's it. And the calculation will be like super easy because what you really need to do is that you just need to calculate the loss for this individual example, right? But only for this simple example, and then multiply n and c, and then plus the gradient of this regularization term. You update the GFW, right? So you don't really need to compute the gradient for 1 billion different examples. So the computation cost is much cheaper. But why can we do this? Why doing this right? Right? Is there any like theoretical or mathematical justification for this? So here we'll give a very brief sketch to explain why doing this is right. This actually explains almost all the current stochastic gradient descent frameworks used in neural networks, using any other models, right? Okay, so in general, let us assume our objective function or our total loss function has this form. F is just the total loss function on some training data set, right? So the loss contains two parts. One is regularization term. It's just like square norm in SVM. You want to penalize over complicated hypothesis space. And also you have some loss term over the training set. And of course, you're going to go through all the training examples in the data set, like big N training examples, right? You calculate the loss on every training example, add them together and multiply a hyperparameter C, right? So if we have a very large N, right, like N is 1 billion or even 1 trillion, calculate one gradient of this f of w will be very costly because you have to go through this big summation, right? How can we simplify this? So we're going to rearrange the form of w in this way. Inside the summation, we multiply the loss over hxn by big N. So remember, big N is the size of the training data. And of course, in our side, I'm going to divide by N. So you can see that N and 1 over N, they cancel out, right? It doesn't change the total loss at all. But what does this guy mean, right? Although it kind of like add a additional term and cancel the additional term outside the summation, it actually brings a probability explanation. What kind of probability explanation? You can view it like for this N training examples, right? You have the equal probability to roll the die. You have like a die which has N points. You have the equal probability to pick up arbitrary point. That means the probability is 1 over N, right? And once you have this pick up a data point, right, you calculate the loss function. So then that means this loss function is a random variable. Why? Because xn itself is randomly selected from you rolling the die, right? So if you want to calculate the expectation of this loss function under your rolling die experiment, it will give this, right? So K here means the index of the data point you choose through your rolling the die, right? And you have the equal chance to select any data point in this whole training set, right? If you take expectation, that means over this N times L xk W. Xk is just the corresponding data point selected by you, right? The expectation will be exactly this guy, right? Just follow the definition. Remember, expectation is the summation of the probability times the function value, the function value over every possible sample times the probability to take the sample, right? And the probability to take the sample is 1 over n, right? And the value of the function for that sample is n times the loss function or xn, right? So that means like by doing this very simple arrangement, you can write your total loss as R of W, like the regularization term, plus C plus some expectation, the expectation for some random variable. Right? So, and the probability of this random variable K takes any value, which is 1 through n, is just 1 over n. It's actually a uniform distribution, right? And of course, because R of W is constant to K, so we can also move R of W inside the expectation. It doesn't change anything because the expectation of constant is still expectation. So then you can write our total loss function as an expectation of R of W plus C times n times this loss over some randomly selected data point with the current model parameters W, right? And in the other side, you're gonna calculate expectation, right? Expectation under how you select those data points. And here we just use uniform sampling. Every data point has the equal chance to be selected. Right? So everybody is comfortable about this formulation or rearrangement of the objective function. Okay, so now it comes to the exciting part, right? If we give an equivalent view, an alternative view of the total loss function, which is the expectation of some R of W plus some loss, right? Now, if you take the gradient of our objective function, that means you're going to take the gradient of this expectation, right? And under mild conditions, especially mild conditions means that you can switch the gradient and the expectation. So basically, you can switch the integral and the gradient. In many cases, you can just switch them. So this gradient of expectation is the expectation of the gradient, right? That basically means like, okay, you can first take the gradient of this R of W plus C times n times the loss over the selected point xk under W. Then you take expectation about how you're going to select those data points. So what's the benefit? The benefit is that actually we can just take out one sample of this gradient. So remember, this becomes an expectation of the gradient. Right? The gradient itself, which is this part inside this square bracket, is a random variable. Why is a random variable? Because it depends on xk, right? Sk is random selected by rolling the die, right? You have an equal chance to select them. So this gradient is random, so we call it stochastic gradient. And because you take expectation of this stochastic gradient, you can recover the exact gradient. Then we call this stochastic gradient as unbiased. What is unbiased? Unbiased random variables just means like unbiased estimate just means like you take expectation of that estimate, you can convert to true value. Right? So here is a gradient, right? If you take expectation of the stochastic gradient, you recover the exact gradient. So this is called unbiased stochastic gradient. And then there's a large literature showing that if you just update your model with stochastic gradient, you don't need to really recover the exact gradient. You just use stochastic gradient to update the model. Then with probability 1, you're gonna also arrive at the minimum of the function. Right? That's how the aforementioned process is valid, right? So if you take a look at the way to compute this stochastic gradient, right? It's like, okay, I'm gonna random pick up xk, right? Random pickup means like I have an equal chance to pick up an arbitrary data point in this entire data set, right? And then I calculate the loss at this data point and then multiply it by the total number of training examples, right? This is like equivalent to duplicating this example xk to fake the full data set, right? And then calculate the gradient of the total loss, right? And doing this can give you an unbiased stochastic gradient. And if you use unbiased stochastic gradient to update the model, you guarantee to find a minimum of your objective function. And by guarantee here, I mean like determinist guarantee is actually meaning with probability 1 or almost surely. And we don't need to know what does mean by almost surely or probability 1 because you have to know some basic concept about like Mayer theory and basic concept in probability measurement. But basically you can be like, okay, in practice, you almost like always find a function minimum with the stochastic gradient. So now going back to this full procedure for the stochastic gradient descent, we can see, right? So every time we randomly pick up an example, xi, yi from the training set S, right? We repeat xi, yi to make a full data set, right? To be the same size of the original data set, and then take the derivative of SVM objective, right? This is a total loss of the SVM objective on this fake data set, which is just a loss over this random selected example, and then multiply the total number of training examples plus C times C plus this regularization term, right? You just take the gradient and doing gradient descent with some learning rate schedule gamma t. And this algorithm is guaranteed to converge to the minimum of the objective function if gamma t is sufficient small. And as to what does it mean by gamma t is sufficient small, we're going to discuss in a minute. But so far, is everyone comfortable? Any question? We see now why we can perform this stochastic gradient descent, right? And actually, you can fabricate or you can craft any loss function like following this structure. You can use exactly the same framework to conduct the training of your own model, not restricted to SVM. Okay. So next, we want to discuss the difference between gradient descent and stochastic gradient descent. Right? So why do we choose stochastic gradient descent? What's the benefit? Right? So to be concrete, right? And gradient descent is like, okay, you have a GPS, right? You can GPS every time you just drive your car toward your house. Right? And using this, like this contours of function values, right? So in the center is the function minimum. And so you can see the contours from outer to inner represent the function values from larger, smaller to smaller to small, right? So if you take the gradient descent, you see that the gradient descent, the direction you move toward is kind of orthogonal to the contour of the function, right? And you always trying to drive toward the function minimum. But what does stochastic gradient descent behave? So one thing we need to be very clear is that stochastic gradient descent, stochastic gradient is not true gradient. Actually, it's very, very inaccurate. Why? Because if you take a look at here, right? So you're just random pick at one example and multiply it for many, many times and calculate gradient. It's definitely very, very different from you calculate gradient for every loss, right? For the loss for every examples and add them together, right? It's very different. So stochastic gradient is very rough approximation of the true gradient. So you can't expect that, okay, they're gonna follow the same direction as the gradient descent. Instead, you see the stochastic gradient descent is quite messy. The update is quite messy. It's like a drunk driver. Like you kind of like you're drunk, but you still want to drive your home, right? Just to drive through your feelings, right? Through your intuition. And the amazing thing is that although you're drunk, you probably random drive north, random drive northeast, and even drive back, right? But eventually, as long as you drive carefully, meaning that every time you drive a small distance, then you you kind of adjust and kind of rest for a while and keep doing that, and eventually you can still arrive at your home. Right? This is typical behavioral stochastic gradient descent. Right? So the updates looks like quite wild, quite messy, but there's a strong theory telling us that you're going to eventually find the function minimum as well. Any questions so far? What number reduce? The number of what? The number of epochs? It's not necessary. Yeah, that's a good point. We'll talk about this during about the theoretical guarantees. Actually, it is possible that stochastic gradient descent has converged, even you don't see all the examples in data set. Like within one epoch, even your epoch has not yet been finished. You have already converged to the function minimum. That's why, like in a large scale data scenario, like people always prefer stochastic gradient descent. Any other question? What? Well, that's a good question. Actually, this is another story, but it's a very difficult question. Like, if the objective function you're minimizing is a convex function, there's no issue, right? Any local minimum is the global minimum. But if your objective function is non-convex, is non-concave, and it's highly nonlinear, many local minimum, and it's hard to say anything. Is maybe you start with gradient descent, you arrive this local minimum, right? But you start with the same place as the stochastic gradient descent, it might arrive at different local minimum. There's no guarantee on this, but empirically, I mean just empirically, like people have found that in super complicated machine learning models like deep neural networks, looks like using stochastic gradient descent is easier for you to find a good local minimum, meaning that the deeper valley of your function is then you just use a deterministic optimization like gradient descent, even second order gradient descent. That's the benefit. Okay, any other question? Okay, next, we're going to address a remaining issue for our SVM objective function, which is called subderivatives. So we have already known how to apply the stochastic gradient descent, optimize our SVM objective function, right? The issue comes from here, right? Even you construct a stochastic gradient, right? Stochastic loss by random selecting one example, right? You will find that the hinge loss here is actually not differentiable, right? There's no derivative for the hinge loss, especially at the turning point, right? So then how do we update the model, right? If we take a look at the hinge loss itself, like with a more clear way, right? What's the derivative of the hinge loss with respect to W? So here comes the problem, right? Now that the true gradient doesn't exist, right? So let us come out some kind of substitute, which also guarantees the descent of the function and also guarantees convergence. So this substitute is called a subgradient or subderivatives. So what is a subgradient? We can view it as kind of a generalization of the gradients to non-differentiable functions. So remember, for a convex function, if it is differentiable, and we know this property is that, okay, you can draw a tangent line at any function body, any point in the function body. We know this tangent line will lie below the entire convex function, right? But then What if this convex function is not differentiable? Like, suppose now I have some like a sharp turning point. Sorry. You have some like sharp turning point here. You actually do not have the gradient, right? But looks like you can still draw some line. Of course, it's not tangent line, but this line can still lie below the whole function body, right? So then we can use that line, its slope in particular, as the subgradient. This is called this is how this subgradient was motivated, right? Informally, a subtangent line at a point is any line that crosses the point of the function body, but still lies below the entire function. Then we call this line as a subtangent line. And the subgradient is defined as the slope of the subtangent line. So let's see examples, right? So here is one convex function f of x, right? So see that at some places f of x are differentiable, like here, x1, right? We know in x1, right? We know f is differentiable at x1, so we can draw a tangent line. This tangent line can be represented in this, right? F of x1 plus g1 transpose x minus x1, and g1 is the gradient of f at x1, right? So g1 is your gradient. Right? But if you look at x2, right? x2 doesn't have gradient. Why? Because the left limit is different from the right limit, right? This is basic definition of the gradient, right? So so basically x2 at x2 function f is not differentiable, but across x2 you can still find many lines which stay below the entire body of f, right? Say I can draw this guy, right? This line, and which is represented by f of x2 plus g2 transpose x minus x2, right? And you can draw this line, fx2 plus g3 transpose x minus x2, right? Actually, there are infinite such lines, right? And all of those lines pass through x2, f of x2, and then stay below the entire body of f, right? So we can choose an arbitrary subtangent line here and use their slope as our subgradient. Okay? For example, you can use G2, you can use G3, or you can use any slope in between. And it turns out that you can use subgradient to optimize the objective function. The convergence guarantees is still there. There's not any change. Is there any relationship between what? It's different, right? It was just I want to show like two different input locations, right? Where at x1, f is differentiable. So you have the gradient, right? You don't need to worry about the gradient calculation issue, right? But at x2, fx is not differentiable. F of x doesn't have any gradient at x2. But we still want to update your model, say at x2, right? Then you can take the subgradient. Subgradient means that, okay, if you can draw a line which pass through x2 and f of x2, but the line stay below the entire function body, like this line and this line, then the slope of this line is called subgradient. You can use subgradient to minimize the function. Yeah, that's a good question, right? And then you kind of oscillate, right? You're gonna, if you use subgradient, you're gonna oscillate surrounding this one, right? And that kind of like you have to use some like a strategy to see like whether your function value change is very, very small. When it's small, you can conclude that okay, you're gonna be very close to the function minimum. You cannot guarantee that you exactly arrive at function minimum because of the numerical system we used. Okay, great question. Any other question? Okay, so now let us apply subgradient to the SVM objective, right? So this max function, we see that is actually a piecewise function, right? So when this 1 minus function margin is less than 0, then function's value is 0. Otherwise, it's 1 minus this guy is a linear function, right? So we can use arbitrary subgradient for this, but here we just use a very simple one, right? We just look at if this max is 0, meaning that we are at this region, then the subgradient is simply 0, right? We just take the slope of this line, right? Of this line, and this line obviously it kind of overlaps part of this max function, but it still stay below the entire function body. So the subgradient is valid, is 0, and then the full subgradient will include the regularization term, which is just the W0 and 0, right? And if your max function value is not 0, it's 1 minus yi W transpose xi, that means you're at this part, right? Now you just use this line as your subtangent line. And this line, again, overlaps part of your max function, but stay below the entire function. So you use the gradient. You use the slope of that line, which is just minus W transpose, minus xi, yi xi. Of course, you need to multiply with c in front of it and n, right? And then you got your full subgradient to be the gradient of the regularization term subtracted by say n yi xi. Okay. So in this way, we addressed the gradient computation issue. We are essentially using a subgradient to conduct the stochastic gradient descent procedure. And next, we just plug in this subgradient calculation into our framework, right? We use the stochastic subgradient descent to SVM, and so here's the stochastic subgradient we computed, right? So initially we set all the model parameters to be 0, and we go through big T epochs over the data set. And in each epoch, we sequentially pass through the training examples, right? For every training example, xi, yi, you calculate the subgradient correspondingly, which is here, right? And you multiply the subgradient by some learning rate gamma t. You update it, right? And here, this updating can be further written in more detail. You have two cases because the form of subgradient has two cases, right? First, if the function margin yi wi xi less than or equal to 1, that means this max function value is the right term, right? It's 1 minus yi W transpose xi. Then your subgradient is this guy, right? And you just subtract it by the subgradient multiplied by gamma t, which is here, right? And otherwise, your max value is 0. Then your subgradient is here. You'll update your W accordingly. Remember, in this case, the subgradient, the bias parameter B doesn't have subgradient. It's 0, right? That's why I only need to update the feature weight vector. So here I want to emphasize that gamma t is the learning rate. There could be many tricks, right? So actually, you need to carefully schedule your gamma t to make sure some conditions are satisfied to get convergence, right? And in practice, to be more stable and converge faster. In every epoch, we usually random shuffle the entire data set, then sequentially go through the training examples to increase the chance that you see as many examples as possible. Okay, so any questions so far for the whole stochastic subgradient descent learning framework for SVM? Okay, so the last thing about this is about how do we tweak the learning rate gamma t, right? As we just mentioned, right, gamma t is learning rate. You have to carefully schedule to make sure you converge, right? So if we can make our gamma t's, those learning rates, satisfy the following three conditions, then with probability 1, almost surely, the stochastic gradient descent or stochastic gradient subgradient descent frame, the procedure will converge to the minimum of the objective function. So what are the three conditions we must satisfy? First, the step size gamma t must be positive. Second, the sum of squares of those gamma t's over t from 1 to infinity is finite. So basically, if you write out explicitly, if you sum over from 1 to infinity of gamma t squared, this guy must be bounded. It cannot be infinite. And third condition asks us, if you just directly sum step sizes over t from 1 to infinity, then this must be unbounded. So that's a very interesting requirement. To sum over gamma t directly, this must be unbounded. So what does this two requirements imply? So the first requirement, the summation of the square of gamma t must be unbounded. Just means that your learning rate cannot be too large. Like this is your value of your objective function, right? If your learning rate is too large because doing stochastic gradient descent, right? It is possible that it's gonna like perturbate and fluctuation forever and ever, and leaving a significant gap from the position you explore to the real function minimum. That's why we require that step size cannot be too large. Otherwise, just jump back and over and back and over, back and over, but never effectively proceed. Okay, then why do we require, if you add up all gamma t's together, they must be bounded, must be unbounded, meaning that it just adds up all gamma t together, it must be infinite. It just wants you to make sure your step size cannot be too small. If it is too small, what consequence will have, right? If it's too small, it is likely that, okay, you're gonna move and just stuck at some places, never move out. Because your step size is smaller and smaller, so it's decaying so fast and such that it cannot go beyond, say, that mountain, right? So you see the requirement, two conditions, right? They actually want to your step size to be enough large, but not too wild. And only under this like constraints, it will guarantee that you have a proper step size schedule, and eventually you are gonna arrive at the function minimum. That's why in practice, we always need to schedule a gamma t to satisfy these three conditions. And here we introduced like two classical ways of doing this scheduling, and you can verify it by yourself. These two schedules both satisfy all the three conditions. You can show it by yourself and practice your calculus 1 and calculus 2. I forgot. I don't know. I forgot when I started to learn series, right? This is actual series. Will converge and not converge, right? But anyway, you can, it will be fun for you to verify this, right? But in the modern stochastic gradient descent libraries, things becomes way more complicated. They have like a per element updating scheme, and I introduce some momentum and to further accelerate the convergence, which we're not going to discuss in this class. Right? But if you're interested, you can take a look at those modern stochastic gradient descent learning algorithm. So here we just want to share some like convergence results and learning rate to answer the question, why do we prefer stochastic gradient descent in the large data scenario? Right? So suppose our goal want to get an accuracy within epsilon. That basically means like, suppose this is your true function minimum, right? I want to know, okay, within epsilon, to arrive at within the epsilon distance to x star, how many iterations do we need? Okay. If your function is a strongly convex function, if you have n examples, and your instance space is d-dimensional, then gradient descent will need this many iterations to get to the epsilon distance within epsilon distance to the true minimum of the objective function, right? So you can see that the number of iterations actually is proportional to the number of training examples, right? And is also proportional to the dimension of instance space, and also proportional to the epsilon. Of course, this is reasonable, right? So the closer you want to get to the ground truth minimum, the more iterations you will need, right? And times this logarithm 1 over epsilon. But if you look at the stochastic gradient descent, the interesting thing here, you see that the number of iterations only depends on the dimension of instance space over epsilon. It has nothing to do with number of training examples n. That's why we favor it so much in the large data scenario, because the convergence here, by convergence, we mean that practically we want our algorithm to stop when you arrive at like epsilon, within epsilon distance to the ground truth minimum, right? So we found that if to achieve the same kind of convergence, actually stochastic gradient descent is not affected by the number of training examples at all. And even better, it is possible that within one epoch, even you haven't passed through the entire training set, you have already converged to the accuracy within epsilon. That's why in practice, people always like stochastic gradient descent. Right? Any questions so far? Okay, so let's stop here today and see you on Thursday.